So section 3.4, combinations and Pascal's triangle and the binomial theorem. So in a previous lesson, we looked at the Pascal's triangle. Is this triangle that you see here on the left with these arrangements of numbers, each number in the triangle being the sum of the two numbers directly above it. And each row in the triangle begins with a 1, and each row in the triangle ends with a 1. We also looked at how to write each term inside the Pascal's triangle with reference to its row number and its position within that row. Now here I'm going to also show you that you can express each number as a particular combination, where the row number is the value for n, and the position in that row is the value for r. Okay, so there is a direct corresponding relationship between t of n comma r, and it is equal to the combination of n choose r. So n c r, or it can be written in this notation, c of n r. Okay, and the same rules that you use to apply for the notation for each term can be also applied for combinations. So I can also say here that n cr is equal to n minus 1 c of r minus 1 plus n minus 1 choose r. Okay, and we can use this relationship and apply it this Pascal's method to any sorts of kind of combinations that we have, not necessarily having to be in the triangle. So here you have 12 choose 8, and I can express this as 1 minus the row that n value, so 11. And we think of the two numbers above it, right? So if you had 12 choose 8 directly above to the left and to the right, I would have 11, row 11 choose position 7, and then row 11 choose position 8. So I can now express this combination formula as 11 choose 7 plus 11 choose 8. Okay. Now these two, think of these two as terms right beside each other in position 5 and position 6 on row 19. They are equivalent to the combination of the next row's terms. So 20 choose 6. Example, calculate the sum of the first 4 terms of the diagonal 2 in Pascal's triangle. So r equals 2. So you look for position 2. So 0, 1, 2 would be over here. It starts here at this 1. And we're looking at every number down that diagonal at position 2. So 1, 3, 6, and 10. So find the sum as it relates to combinations. So we're looking at 1 plus 3 plus 6 plus 10, which is equal to 20. As a combination, we can express this as 6 choose 3. Just based on, how do I know this? It's based on the combinations of each term. So we have row 2, choose position 2, plus row 3, choose position 2, plus row 4, choose position 2, plus row 5, choose position 2. And that's going to be equal to 6 choose 3. Let's look at another example. Calculate the sum of the first 5 terms of diagonal 6. Find this value in Pascal's triangle and relate it to n choose r. So in diagonal 6, all your r values are going to be 6, r equals 6. Now diagonal 6, where does that begin? Which row does it begin? If this is row 0, this is row 1, row 2, row 3, row 4, row 5. It's going to begin in row 6, because remember the positions start also from 0. So this is 0, 1, 2, 3, 4, 5. So position 6 has to be on the 6th row. So along that diagonal, I'm going to be adding 6 choose 6. Plus 7 choose 6. Plus 8 choose 6. Plus 9 choose 6. Plus 10 choose 6. These are the first 5 terms along the diagonal. which will be equal to 11 choose 7. So all of this, if I add them together, I'll get 1 plus 7 plus 28 plus 84 plus 210, which is 330. The binomial theorem. So recall that a binomial is a polynomial with just two terms. So that it has the form a plus b. This is a binomial, if you recall. And a and b are terms. It can be with coefficients and variables. And so I can expand something that looks like a plus b raised to an exponent n with using Pascal's triangle, right? So just looking at very simple ones here. So you might remember from our previous classes, so a plus b to the power of 0 is equal to 1. A plus b to the exponent 1 is just a plus b. And a plus b squared, if you expand it using FOIL or the distributive property, you get a squared plus 2ab plus b squared. And you could also do a plus b cubed, and then so on and so on. But if you look at carefully at the pattern of the coefficients, you'll notice that here I have a 1. The coefficients here are 1 and 1. Here I have a coefficient of 1, 2, and 1. Here I have a coefficient of 1, 3, 3, and 1. So what do you notice? It looks like they follow the Pascal's triangle. Like so. So there must be a relationship between expanding a binomial and the coefficients found in Pascal's triangle. So notice that in each successive term, the exponents on the a decrease by 1, while exponents on the b increase by 1. So even here a cubed, then I have a squared, then I have a, and then I have no a. Here I have b cubed going backwards to b squared, then b, and then no b. So the coefficients of each term in the expansion correspond to the terms in row n of Pascal's triangle. We can write these coefficients in combinatorial form using the binomial theorem. So we're going to use the pattern to expand a plus b to the exponent 4. Okay, so you start off by writing a to the exponent 4, then a to the exponent 3, then a to the exponent 2, a to the exponent 1, and then a to the exponent 0. And then going backwards, I start with b to the exponent 4, b to the exponent 3, b squared, b, then b0. And then row 4 in Pascal's triangle, what are the coefficients? In row 4 we have 1, 4, 6, 4, and 1. And those are going to be my coefficients. So 1, 4, 6, 4, and 1. And I just put some plus signs in between each term. And there you go. That's the expanded form. Now in proper mathematical form, we don't need the b to the power of 0. We can erase that. And we don't need a to the power of 0, we can just erase that. So since each term in Pascal's triangle is related to a combination, you can use the binomial theorem to expand any power of a binomial expression. So even if you're going into deep number of rows in Pascal's triangle, you don't need memorize these actual coefficient values. You can just use the combination values. So as long as you know what row number you're in, you can use combinations to help you find those coefficients. Okay, and the n value exponent will correspond to the row value in Pascal's triangle. So in this example, expand x plus y to the exponent 6. We're talking about row 6. Okay, and the coefficients in row 6 are 1, 6, 15, 20, 15, 6, and 1. And if you don't remember those or don't memorize those, you can easily calculate them using combinations. So here I have 6 choose 0, 6 choose 1, 6 choose 2, 6 choose 3, 6 choose 4, 6 choose 5, and 6 choose 6. Okay, and then after you have those coefficients, you can now expand your binomial. So follow the pattern. Start with the first one, x. So x to the power 6 plus x to the power 5 plus x to the power 4 plus x to the power of 3 plus x to the power of 2. And I should have left some more room here, so let's just rewrite this. So x5, x4, x3, x2, x1, and x0. Going backwards, we have y6, y5, y4, y cubed, y squared, y, and y0. And then my coefficients. So 1, 6, 15, 20, 15, 6, and 1. And then put your signs in between. And there you go. That's your expanded form. Clean it up a little bit. You don't need the y0s. You need the invisible. You can make the ones invisible. So x to the power 6 plus 6x5y plus 15x4y squared plus 20x cubed y cubed plus 15x squared y4 plus 6x y5 plus y6. Now what if your binomial has a minus sign? Okay, just ignore the coefficients for now. We'll just expand using the what we know. So we have here, let's ignore coefficients to start. Okay. Actually, no, let's do it. Let's just write down. Let's do everything. Let's do it properly. So 2x minus 1 to the power 4. So a is going to be 2x. B is going to be negative 1. So I'm going to start off with 2x to the power 4. So 2x to the power 4, 2x cubed, 2x squared, 2x1, 2x 0. And going backwards, I have negative 1 power 4, negative 1 cubed, negative 1 squared, negative 1, and negative 1 to the power 0. And then what are my coefficients from Pascal's triangle? Well, for row 4, we know they are 1, 4, 6, 4, and 1. So here I'm going to write 1, 4, 6, 4, and 1. Let's put some plus signs in between all of these. And then we simplify. Now be careful when you simplify, some of these plus signs might turn into minus signs. So 1 times 2x to the power 4 times negative 1 to the power of 0. So negative 1 to the power of 0 becomes 1. So here I have 2x to the power 4. Then I have 2x cubed. Well, 2 cubed is 8. So, and then I have a minus 1 in front, so I'm going to have a minus. This is going to change to a minus. And 4 times 8 is going to be 32. And I have also my x cubed. All right, negative 1 squared is just a 1, so that goes away. And then I have 2 squared is 4 times 6 is 24, so 24x squared. And then I have negative 1 cubed is negative 1, so that will change the sign here. And 2x to the power of 1 is just 2x, and 2x times 4 is 8x. Then I'll have negative 1 to the power of 4, which is just positive 1, and then 2x to the power of 0 is also positive 1, and then we have 1, so plus 1. And then there's my answer. I made a mistake here. 2x squared, this should be 16. So 2 to the power of 4 is 16 when I remove the brackets. All right, expand 3x plus 2y cubed. So again, write them in order. So 3x cubed, put them in brackets first. Then we have 3x squared. We have 3x to the power of 1, and we have 3x to the power of 0. Going backwards, we have 2y cubed, 2y squared, 2y, and then 2y to the power of 0. What are my coefficients for row 3? Well, they are 1, 3, 3, 1 from Pascal's triangle. So I have 1, 3, 3, 1. Plus signs in between. And then we simplify. Anything to the power of 0 is 1. Anything to the power of 0 is 1. So here I have 3x cubed. So 3 times 3 times 3 is 27x cubed when I remove the brackets. Then I have 3 times 2 is 6. 3 squared is 9, so 9 times 6 is 54, so plus 54x squared y. Then I have 3 times 3 is 9. 2 squared is 4, so 4 times 9 is 36. A single x, and then a y squared. And then finally, 2y cubed, so plus 2y cubed. Sorry, 2 cubed is 8, so 8y cubed. And there you go. So don't forget to cube it after you remove the brackets. And that's it.